In this video, we present a simple training of an AI transformer to play tic-tac-toe in C++. When finished, the program plays the game like this. Try again. Billy will first explain to you how this is done.
As we just mentioned, we'll talk about how to train a transformer to play tic-tac-toe. It's kind of a recap of what we covered in the past few videos. The tic-tac-toe game is played on a 3x3 grid. Two players play against each other. One player uses X, the other uses O. The objective is to be the first player to get 3 of the marks in a row, horizontally, vertically, or diagonally. The rules are that X usually goes first. Players take turns placing their mark in an empty square. The game ends when a player gets 3 in a row for a win. Or all 9 squares are filled without a winner, which is a tie or a draw. With perfect play from both sides, tic-tac-toe always ends in a draw, which is why it's a great simple game for teaching AI concepts like game trees and minimax. You could refer to these 2 links about playing tic-tac-toe against an AI agent. The video A Hello World example of AI game in C++ explains the concept of a game tree and the minimax algorithm, demonstrating how minimax can be used to generate optimal moves for a game of tic-tac-toe. The video training a neural network to play tic-tac-toe in C++ builds on this foundation, showing how the minimax algorithm can be used to train a multi-layer perceptron to play tic-tac-toe. Following a similar approach, we train a transformer to play the game. However, instead of relying on minimax, we will use a simpler method to generate the training data for the transformer. We've discussed how to implement both a simple decoder-only transformer and an encoder-decoder transformer. If you want to see the code in action, you can refer to these 2 videos. A simple GPT-style AI transformer in C++ walks you through a full but easy-to-follow implementation of a decoder-only transformer. It includes a simple working example and also covers the pros and cons of this design. It's a great place to start if you're new to transformers. Once you're comfortable with the decoder-only version, check out this next video. A full encoder-decoder AI transformer in C++. It shows you how to build a complete encoder-decoder transformer and demonstrates several simple examples of using it for different tasks. Feel free to watch these in order, as the second video builds on ideas from the first. So, when should you use which? Use a decoder-only transformer, like GPT, for tasks that generate text step by step, such as chatbots, story generation, or code completion. Use an encoder-decoder transformer, like the original transformer model, for tasks where you need to transform one sequence into another, such as machine translation, text summarization, or question answering. In short, if your input and output are in different languages or formats, go with encoder-decoder. If you're generating new content from scratch based on a prompt, decoder-only is usually the way to go. For the game of tic-tac-toe, a decoder-only model is the more natural choice because we want to predict the next move based on the previous moves. In other words, given a sequence of past moves, we calculate the probability distribution for the next move. This type of autoregressive prediction is exactly what a GPT-style, decoder-only, transformer is designed for, making it ideal for the task. Here's a simple example. Suppose the game has progressed with the moves, X takes center, O takes top left, X takes bottom right. The decoder-only model looks at this sequence and asks, what is the most likely next move for O? It outputs probabilities for each empty square, and we pick the highest one, or sample from the distribution. How does this compare to an encoder-decoder transformer? An encoder-decoder model would be overkill for tic-tac-toe. It is designed for tasks where the input and output sequences have different structures or lengths, such as translating English to French. In tic-tac-toe, both the input, past moves, and output, next move, represent the same thing, positions on the same board. There's no need for a separate encoder to process the input and a decoder to generate output. A single decoder that predicts step by step is simpler, faster, and perfectly sufficient. In short, decoder only. Great for turn-based games, text generation, and anything where you predict the next item in a sequence. Encoder-decoder, better for transforming one full sequence into another, like translation or summarization. So for our tic-tac-toe transformer, decoder only is the way to go. When training a transformer to play tic-tac-toe, we represent each move as a token. The board consists of 9 squares, labeled 0 through 8, and each token corresponds to marking a specific square. In this representation, tokens 0 to 8 represent placing a mark on the corresponding square. For example, token 0 means mark square 0, token 1 means mark square 1, and token 8 means mark square 8. Token 9 represents the start of sequence, SOS, signaling the beginning of a game. Token 10 represents the end of sequence, EOS, signaling the conclusion of a game. This compact tokenization allows the transformer to learn optimal move sequences through autoregressive prediction, where each token conditions on all previous tokens in the sequence. We could use the minimax algorithm to build a training database, as it can generate all optimal moves for the game. However, for simplicity and for demonstration purposes, we will build our training dataset manually, by playing the game ourselves and saving the data to a text file. Interested viewers can always add more data to the file and run experiments with their own custom datasets. To support this, we have created a simple graphics program using OpenGL which has been used in a previous video. It allows a user to play the game interactively and automatically collects the gameplay data into a text file for later training. Let's copy, compile and run this program.
So we copy this program and place it into a connect data file and save it. We have a script to compile this, so execute this script. So we have generated the executable connect data. Now we can execute it. As it says here, P is to play the game, R is to reset the board. So I press P. So it has X at the center, and we can click here and click another X, O here, X, and suppose I click the O here, sorry, X here and O here. Okay, so it was a jaw. Now let's try another one. This is just for demo. We said play. X. X. Okay, so AI has 1. This is just for demonstration. And then escape. So these are the 2 sequences that we have saved. And it is saved in the file data.txt. Okay. So the 11 here means there are 11 tokens in this sequence. Okay. The 9 is the start of the sequence, and these are the moves, and 10 is the end of the sequence. Okay. So totally 11 tokens, and this means 7 tokens, okay. And these are the moves. It starts from X. Okay.
Below is the code for the transformer classes, utility functions, and their corresponding header files, all of which we have largely discussed in previous videos. We define player as an enum with 3 elements, empty, X, and O. By default, empty is assigned the integer value 0, while X and O are automatically set to 1 and 2, respectively. We have added 2 utility functions for matrix persistence. Save matrix writes matrix elements to a file. Read matrix reads matrix elements from a file back into a matrix. We do not present the code for the tokenizer class, as it is not needed for this context. We have also added weight persistence functions to our transformer, which we refer to as mini-GPT. Save weights saves the weights of each layer to a file. Read weights reads previously saved weights back into the corresponding weight variables. Below are the functions and main routine used to test the training of our transformer for playing tic-tac-toe. Database is a vector of integer vectors, specifically, a collection of sequences, where each sequence is a vector of tokens. The build database function reads sequences of tokens from a file and stores them in a database object, DB. The generate function produces tokens using the transformer model via a greedy algorithm, starting from a source prompt. It operates as follows. Uses greedy decoding to select the next token at each step. Appends each newly generated token to the current sequence. Terminates when either the maximum sequence length, max_len, is reached, or the end of sequence, EOS, token is generated. The predict move function returns the next token specifically, the legal move with the highest probability according to the transformer model. The main function can be run with or without an input argument. If an input argument is provided and its value is larger than 0, the program is run in training mode and the newly trained weights will be saved in the file data.txt. Otherwise it is run in playing mode, which reads in the pre-trained weights from the file data.txt. After training or weights are loaded, it generates a test sequence beginning with the prompt SOS 4, 2. The program then initiates an interactive game where the AI agent, transformer, moves first, always playing the center square, position 4. The initial move is recorded in the history sequence as the prompt. The program waits for the user to enter a valid move and appends it to the history. The program calls generate with the updated history as the input prompt when generating the AI's response. If the next move in the returned sequence is valid, play continues normally. If the move is invalid, the program calls predict move to obtain the next move. If predict move still returns an invalid move, the program falls back to get move to find an appropriate valid move. Here's a make file for compiling the programs. We also provide a main program that allows users to play the game with graphical interfaces. This program does not train the transformer. It just read in the pre-trained weights to play the game. We have copies all files to this directory. This is a small sample of token sequences we have created and saved in the file data.txt.
We have copied all the files to this directory. Now let's compile them. Make. So we created the executable test main. Let's execute it with an input argument 1, meaning we want to train the transformer. So the number of training sequence is 13, and as you can see, the entropy loss decreases along the training, and after about 250 pulses, it decreases below 1, and at the end is about 0.6. Okay. So this is the testing for inference. So the source sequence is 942, and it generates this token sequence. And now it presents a board for us to play, and AI moves first with X at the center. Okay. So suppose we input 8, okay, and AI moves 2. Suppose we input say 6, and AI moves 7. Suppose we input 1, so AI moves 3, and so we do 5. So this is the sequence generated, and it's a job. Now we can also play without an argument. But this is the way.txt file it has generated. So you can take a quick look. Okay, these are the ways. And now, if we run it like this, so that means we run the program without training. Okay, it just reads the ways from what we had saved. Okay. Suppose again in the moves, okay, AI moves first. Okay, at the center, suppose we go 1, okay, and AI moves 3. Suppose we do 6. And then 5, and 2. So this is just a demo. Okay, so you could try that yourself. We can also compile the graphics program. Okay. The test main g.cpp. And we have written a simple script to compile this. Okay, basically it links test main g with other object files we compiled, and also link with the graphics library. So we just compiled. Okay. So it compiles and generate this executable, so we can execute it. Text main G. So this won't do any training. It just let you play. If it's in the ways and use the transformer to play with the user. So P, when we press the key P, we play the game. R is to reset the port. So now I press P. So again, AI moves first with X, and suppose again we click on this. So AI moved at this, and suppose I click on this. AI moves here, and suppose I clicked here. So AI moves here, so I click here, so it was a draw. And now we can reset the port, and play again. And suppose I do 1, and do this, and then we do this. Well, suppose we purposely do this, so the AI 1, and so you can try that yourself, and you could always add more data to the training file by painting the game. Remember, we have this contact data that you can always add more data to it. So this wraps up our discussion on this topic. So thank you for watching.